Today, we're stepping inside the lab to uncover the hidden code of safety that lets scientists work with some of the most dangerous materials on Earth. Let's dive right in.
I mean, really think about that for a second. A laboratory is one of the few places where you'll find powerful acids, flammable solvents, high-voltage gear, and invisible radiation all in the same room. So what is this hidden code that prevents total chaos and actually makes discovery possible? Well, it all starts with the very first thing you put on.
And that first line of defense is, of course, personal protective equipment, or PPE. You can think of it as the armor scientists wear into battle every single day. But here's the thing. Not all armor is created equal, and picking the right piece is absolutely critical.
Just look at the difference here. On one side, you've got your standard safety glasses. They're great for stopping something solid from flying straight into your eye. But check out the goggles on the other side. If you're working with chemicals, you need that complete seal around your eyes. A single splash of a corrosive liquid could easily get right around regular glasses.
The same idea applies to your hands. Glove thickness is measured in mils, that's 1/1000th of an inch. A thin nitrile glove under 2 mils is perfectly fine for a lot of tasks. But if you're handling strong acids, you're going to want double that thickness to keep that chemical from just eating right through. It is a tiny measurement that makes a huge, huge difference.
And, using them correctly is just as important as picking the right ones. These might seem like really basic rules, but they are what prevent cross-contamination. You check for holes, you never ever reuse them, and you always wash your hands after. A simple tear or reusing a contaminated glove could wreck an entire experiment or, way worse, expose you to something dangerous without you even knowing it.
Okay, so once you're all suited up, the next big challenge is the chemicals themselves. This is where we get into how you manage the built-in chaos of all these volatile substances.
And the stakes couldn't be clearer. It's not just about what a chemical can do to you, it's what chemicals can do to each other. This isn't just a friendly suggestion, it's a fundamental law of the lab. Mixing the wrong things, even by accident, can have literally explosive results.
So the solution is actually pretty simple: segregation. You keep the acids away from the bases, solvents are kept away from both, and those strong oxidizers, we're talking chemicals that can make fires burn way more intensely, they're kept separate from everything. Storing them in special cabinets, often with plastic tubs inside for what's called secondary containment, makes sure a single leak doesn't start a dangerous chain reaction.
And this idea of safety also covers something as simple as moving a chemical from point A to point B. Carrying a big glass bottle of acid in your hands is just a disaster waiting to happen. One slip, and you don't just have a broken bottle, you have a major chemical spill. That's exactly why designated carriers or carts are completely non-negotiable.
Which brings us right to our next section. The experiment might be over, but believe me, the danger isn't. Now you're left with hazardous byproducts, and you have to have a plan for when things, inevitably go wrong.
I absolutely love this quote from the source material. Don't cook unknown soups. It's a really memorable way of stating a deadly serious rule in hazardous waste disposal. You just can't pour all your leftover chemicals into one big container.
And here's why that is. Different kinds of waste need completely different disposal methods. So chlorinated solvents are treated one way, acids another, waste with heavy metals yet another. If you create a mystery soup, the disposal facilities literally cannot accept it. Why? Because they have no idea how to handle it safely. It becomes this massive, expensive, and dangerous problem.
And if a big spill does happen, the protocol is clear and it's immediate. This is not a job for a paper towel. The #1 priority is human life. You get everyone out of the area, you pull the fire alarm to alert the whole building, and you let the trained emergency response team handle the containment and the cleanup. No heroes.
All right, now let's shift gears and talk about the dangers you often can't even see. Things like fire, electricity, and radiation. They're all forms of energy that pose a huge risk if they're not managed correctly.
Even with something as familiar as a fire extinguisher, you have to use the right tool for the job. Take a look at that row for water. It's great for paper, right? But it is incredibly dangerous for an electrical fire because water conducts electricity. That's why labs use specific types like CO2 or dry powder extinguishers, which are safe for all sorts of different fires.
Most of us know these electrical safety rules, but in a lab, they become life or death. Using properly grounded plugs, that's that third prong that safely diverts electricity if something goes wrong, and avoiding overloaded power strips isn't just a good idea. It's what prevents equipment failure and deadly shocks.
And then you've got radiation. Whether it's coming from an X-ray machine or a powerful laser, the damage can be silent and fast.
Damage to your retina from a laser, for example, is very often permanent. There's no fixing it.
So, scientists follow this really simple but powerful principle, ALARA. It stands for as low as reasonably achievable, and it really just boils down to 3 things you can always control. Minimize your exposure time, maximize your distance from the source, and use the right shielding, whether that's a lead vest for X-rays or special safety curtains for lasers.
So, as you can see, lab safety isn't just some long list of don'ts. It's a carefully designed system. It's the whole framework of control and preparation that allows scientists to work confidently right at the edge of the unknown, turning potential chaos into real discovery.
And this brings us to one last thought. We've just gone through the code from managing extreme hazards in a controlled environment. So it kind of makes you wonder, right? What are the invisible chemical, electrical, or even biological risks that we all navigate in our daily lives without a formal rulebook? And how do we build our own foundations for safety? Thanks for joining me on this one.